Hello, Prof. Mo here of chemjoint.com. I'm going to describe the strength of acids and bases based on pKa value, Ka value, Kb value, pKb value, or pH. So we will determine the strength of acids by some calculations, including these units here. Okay, so just to remind you, strong acids completely dissociate in water to give hydronium. So if you put HCl in water, the water will play the role of a base, picking up that hydrogen. Chlorine falls off, and we use one sure arrow telling us you are sure to form the product H3O plus, what we call hydronium, and Cl that fell off. We discussed this process in a different video. If you had a weak acid like ethanoic acid and drop it in water, water will still play the role of a base, using its lone pair to form a bond between the oxygen and this new hydrogen, and these two electrons will be thrown onto the other oxygen. This is not sure to happen because the acetic acid is a weak proton donor. However, the small part of it that does it gives you a conjugate base, that's the acetate, and again you get hydronium. Weak acids will ionize partially to give you hydronium. Strong acids will ionize completely to give you lots of hydronium. Now, when talking about a generic equation of an acid, let's say we have this acid where this will be the conjugate base, just like here Cl is a conjugate base. If water takes out that hydrogen and this conjugate base falls off, you get A minus and hydronium. You can get an expression of Ka. If it's at equilibrium, then the concentration of products is equal to concentration of reactants. Products are what you have on the right, reactants are what you have on the left. However, there are times that it's not the concentration on either sides are not the same. Only at equilibrium, then they will be the same. At any other concentration conditions, the dissociation constant Ka will be expressed as still the multiplication of the concentration of the products divided by the multiplication of the concentration of reactants. Now you see, water used to be here. We just multiplied on both sides to get this expression, which we call Ka. Okay. Alright, so Ka is given by that expression for this equation. And if you know Ka, you are able to find pKa, because pKa equals to negative log of Ka. Usually, weak acids will have high pKa, and that means inversely they will have low Ka values. See, you are using the pKa and Ka to quantify the strength of acids and bases. And you can imagine, if we are talking about base, we would call this pKb, and it will be negative log of Kb. Okay. Alright, so let's see examples of these strong acids and bases. Here you have a table of a strong acid and a weak acid compared. Okay, so we have strong acids compared to weak acids with their pKa's. So let me cut the table like this. Okay, sulfuric acid has -10. We say the lower the pKa, the stronger the acid. So acidity increases like this, because that's -10 and this is -1.5. Okay, there are factors that make sulfuric acid more acidic. It's because once it loses a hydrogen, it's going to be very resonance stabilized, You can draw resonances. We talked about those factors in a different lesson. And other reasons that make it more acidic. Okay, so the more negative the pKa, the more stronger the acid will be. These acids right here, they have higher pKa. They are weak acids. They ionize partially. See, acetic acid is right here. We just talked about it. It's right there. It partially ionizes. So will HF, HCN, phenol, thiol, and water. Those are very weak acids. Okay, that's a table just showing examples of strong and weak acids based on pKa values. All right, so let's do some calculations. Let's say that you made a solution of your acids in water. Let us do a calculation example of a strong acid. In this case, our strong acid of choice is HCl. HCl. What is the pH of a 2 molar solution of hydrochloric acid? What is pH in the first place? pH is the concentration of protons. How much H pluses you have. That's what we call protons in solution. The expression for pH is pH equals to negative log of H plus. Since it's a strong acid, we can use this expression already. Negative log concentration of H plus. Okay, we are given that the acid concentration is 2 moles per liter. We know that when HCl is put in water, it's gonna ionize to H plus or hydronium and Cl minus. So yeah, that 2 stays. Our equation that we'll use is pH equals to negative log of the concentration of the acid, in which case it will be negative log of 2.0. That's what we were given. And so the pH of the solution having 2 molar of sodium of HCl, having 2 mole of HCl will be, punch in your calculator. I hope you know how to use your calculator. Will be negative 0.30. Quite acidic. Okay, we used this equation directly because we knew HCl is a strong acid. If it's a weak acid, you want to do something else, ice chart. In this example, let us consider the pH calculation of a weak acid. Okay, what is the pH of a 2 molar solution of acetic acid? We know that acetic acid is a weak acid, and because it's a weak acid, it will partially ionize. So we don't expect to have all the 2 molar concentration of the protons in solution. We do not expect that because it partially ionizes. So we come here and say, okay, we know it's a weak acid. We are given the ionization constant. We're given the pKa value, and you can see it's quite a small number. It's quite a small number. It's 1.7. You're given Ka equals to 1.75 times 10 to the power negative 5. Remember our ratio. Ka was equal to concentration of products divided by concentration of reactants. So if this number is quite small, what this means is that you have more of the reactants than the products. You're not really forming products. You're not really ionizing. So acetic acid is a weak acid, and if I want to find its pH, I will want to generate ice chart. So when you put acetic acid in water, it partially ionizes to give me H3O plus, which is the acid, and then it gives me the conjugate base. Okay, so now ice chart, I stands for initial. So initially I had 2 molar, but that 2 molar will slightly change by a value we don't know. negative x, and then we're going to get to the equilibrium, which is E. We will use the equilibrium values to determine the acidity. So I'm writing here 2 minus x because I'm saying if this was the initial and this is by how much it changed, therefore I can easily say what I'll end up with is 2 minus the change. Water does not have a concentration. So initially it was 2 for acetic acid. It's gonna change by a value of x. The concentration will reduce by a value of x as you make products. And then at equilibrium when the change is done, the concentration of acetic acid will probably be 2.0 minus x. On the product side, initially we have not formed any hydronia, we have not formed any acetate, but when the acetic acid changes concentration by a value of x, this will increase by a value of x, this will increase by a value of x. So at equilibrium, you add 0 and x, the change, you'll get x here and x there. Now remember we said that Ka, Ka equals to the multiplication of the concentration of products divided by multiplication of concentration of reactants. So my Ka, which is 1.75 times 10 to the power minus 5, must be equal to x dot x, the products, over reactants, which is just the acid itself, because like I said, the concentration of water is unity. So it will be x squared over 2.0 minus x. Now, because you see that the Ka value is quite small, 1.75 times 10 to the power negative 5, we expect this change to be quite small, that I should simplify this expression to x squared all over 2. That helps me to avoid too much quadratic equation or factorization. So let's find the value of x, and that will give us the concentration of the acid, and then in turn we'll come now and use the pH expression. If you do your calculations, remember you're considering this value and this expression right here. If you do your calculations, you find that x will be equal to 0.00591608. Okay, now that represents the concentration of H3O plus, which of course is just the concentration of the proton. So to find the pH, which is gonna be equal to negative log concentration of H3O plus or H plus, it will be negative log of this number. You'll find that the pH of a 2 molar solution of a weak acid, acetic acid, will be roughly 2.2. The pH of that solution will be roughly 2.2. That's a bigger number than what we got for the 2 molar solution of HCl. For HCl, it was negative 0.3, telling you that HCl is a strong acid. The stronger the acid, the lower the pH value. Okay. What if you are asked to determine the pH of a strong base? The strong base here is sodium hydroxide. Strong base here is sodium hydroxide. Sodium hydroxide is one of the strongest bases because it completely ionizes in water to give you OH, a lot of OH. So when you put sodium hydroxide in water, you'll get Na+. So if it's dissolved in water, you get Na+ and OH-, a lot of it. So since it's a strong base, we may want to do something here. It's a base, it's not an acid. So instead of using the pH equals negative log of H+, we'll use POH equals to negative log of OH-. Okay, this is the count of the concentration of pOH is the determination, is the value for the concentration of OH in solution. So let's first find pOH. Let's first find pOH, and we'll use that to find pH using another expression. So pOH equals to negative log of OH. We are using this again because we have a base. pOH will be equal to negative log of 2, and that is negative 0.3. Okay, but that is pOH. To find pH, we know that pOH and pH should sum up to 14, this expression right here. But we are given the pOH as the answer here, so we'll say that to find pH, it's gonna be 14 minus pOH, which will be 14 minus 0.3, which is 14.3. Quite basic. The pH of a 2 molar solution of sodium hydroxide is 14.3. What if you have a weak base? Then you'll have to use ice charts like we did for ethanoic acid. So here you are asked to find the pH of a solution of NaCN. That is not a strong base. It's a weak base. It's a weak base because it does not completely ionize in water to give you OH minus. So in that case, we will have to use some sort of ice chart to determine what's happening here. So here, this is ionic, exists as Na plus and Cn minus. So since you are thinking base, we'll say suppose that you have Cn minus, okay, in presence of H2O. Since this is a weak base, it will barely take out a hydrogen from water to give you OH minus, and itself being changed to HCN. It will barely, because it's a weak base. Remember that. It's a weak base. Okay? So in that case, I have to use an ice chart because there is minimal change in concentration of the original substance. So initially the Cn minus is 2 molar solution, and then the water of course has unity concentration. You have not formed any product, and then there's gonna be the change in the ice chart. Again, we say minus X for the starting material, and then you start getting some of the product plus X plus X. Plus means it's formed, minus consumed. At equilibrium, when the process is done, the concentration left for Cn minus will be 2 minus X. Okay, while the concentration, we are just adding 2 molar and minus X, you'll get 2 plus minus X, which is 2 minus X. And for the product, 0 plus X gives you X, 0 plus X gives you X. Okay, now we need to use these expressions like we did, but we have to use them in the form of Kb, not Ka, because we are talking base. But are we given Kb value in the problem? No, but we are given Ka. We know that Kb times Ka should be 1 times 10 to the power minus 14, which is what people call Kw, ionization of water. So I can use this expression to find Kb. Kb will be equal to 1 times 10 to the power minus 14 divided by Ka value, which is given in the problem, which is 1 exponent minus 14 divided by Ka value is 4.9 times 10 to the power 10. You'll find Kb to be 2.04 times 10 to the power negative 5. Okay, so we'll say that Kb equals to concentration of products, in this case is XX, divided by concentration of reactants, which is X squared now over 2 minus X. Again, there's minimal change because it's a weak base. Simplify the expression to be S squared over 2. And you remember that your Kb is what you found up there, 2.04 times 10 to the power minus 5. Now solve for X, just using this expression here. solve for x, you'll find that x will be equal to 0.0063875. That is the value of the concentration of the hydroxide, which will help us to find, once we find the concentration of the hydroxide, will help us to find pOH, and then to find the pH, we'll insert our answer on here, 14 minus pOH, we get the pH. Okay, so this equals to, or is equivalent to, the concentration of hydroxide in solution of this weak base. So let's find pOH. pOH will always negative log concentration of OH. In this case, it's negative log of 0.0063875. pOH will turn out to be 2.195 about. So to find pH, we know that pH plus pOH equals to 14. So pH equals to 14 minus pOH. And in this case, it will be 14 minus 2.195. Our grand final answer of pH is 11.8. That gets us to the end. We had to do all this through the ice chart because we have a weak base, which is the same thing you want to do if you had a weak acid. Similar thing, not the same, similar thing. Okay, I hope now you understand how to determine the strength of acids and bases based on their Ka, pH, pOH values. Okay.